Okay, so this will be video number 4 for section 4.3. We pick things up on number 7, and it says use analytic methods to find the intervals on which the function is increasing, decreasing, concave up, concave down, and then find local mins and maxes and inflection points. So what that means is we're going to answer all of those questions using the first and the second derivative tests. So that means I'm going to need the first derivative. And the first derivative is 2x minus 1. And while we're at it, I might as well find the second derivative because I'm going to need it. So the second derivative is simply the constant 2. Alright, so now we want to do my first derivative test, which simply means we need to figure out when my derivative is positive, negative, derivative, and 0. Alright, and so in analyzing my first derivative, I first want to figure out the critical values. So where is the derivative equal to 0? And it looks like I'm going to get one answer. Add 1, divide by 2, I get a half. I should also consider when is the derivative undefined, but that's never, because it's simply a linear function. So hopefully, we have no new critical values from that. So that means for my sign chart, the only thing I need to put on here is a half. At a half, and again we're talking the derivative sign chart, at a half we already know that the slope is 0. The derivative is 0. So then we pick a number greater than a half, plug it into my derivative, and I get a positive number. Plug a number less than a half, like 0, in, and I get a negative number. So I am already ready to answer 4 of my questions. And those are, where is my function increasing? And that would be where the slope is positive. So that's going to be from 1/2 to infinity. Where is it decreasing? And that would be from negative infinity to a half. I can skip down and answer my local min and max questions. We have a slope of, let's see, negative, so we're going down, and then we have a slope of positive, so we're going up. In between it's 0, so that tells me I have a local minimum. So I have the point 1/2, comma, and then I'm going to need to find that y value. And again, some of you are struggling with where do I plug things into, and really it's a question that needs to be answered with a question, which is, what is it that I'm looking for right now? I'm looking for a point. I have the x value. I need the y value. Well, the y comes from the original equation where it says y equals. Y prime equals, that's code word for slope equals. We don't want slope right now. We want y value. So I'm going to plug 1/2 back into the function, which is going to be something like, let's see, 1/4 minus a half minus 1. So 1/4 minus a half is negative a fourth minus 1. So it looks like, quick math, I could be wrong, looks like negative 1 and 1/4. And I'll let you find all the other y values. I'm not going to do any more of those. Local maxes, we don't have any. We're going down, then we're going up. So there are none. So my first derivative test answered 4 of my 7 questions. My second derivative test will answer the rest. And the second derivative test is exactly the same as the first derivative test, except we're using the second derivative to do the analysis. So when is my second derivative, which equals 2, when is it equal to 0? And that, of course, is never. When is my second derivative undefined? And again, that's kind of a dumb question because it's always equal to 2. So again, what it comes down to is I have no places where I'm going to change concavity. But we still want to look at a sine chart. This time it's a sine chart of my second derivative. And I don't have any number to put on here. So what that means is whatever the concavity is at any point, it's going to be the same concavity everywhere. Since my second derivative is a positive 2, then I know that my second derivative is always positive. Meaning, I'm concave up everywhere. And I'm concave down nowhere. And where are my inflection points? Where am I changing concavity? I'm not. So I have none. And that was weird. Let's shrink this back down here. That means that if we were to look at this graphically, again, think about the picture. It's just a parabola, y-intercept of -1. The local min should be my vertex. I have a graph that should look about like this. I found my local min right here. No local maxes, increasing, decreasing. I'm always concave up. I'm never concave down. No inflection points. So the graph matches what we've found. Okay. Let's move on to question number 8. I would encourage you to stop the video at this point and try number 8 on your own if you haven't already done so, and then go through and see if we match. Okay, so number 8, I'm going to need the first derivative. So I'm going to get -6x squared plus 12x, and then my second derivative is -12x plus 12. So now it's time for my first derivative test. When is my derivative, which I'll just write it right here, when is the derivative equal to 0? And when is the derivative undefined? Again, it's a polynomial. There's no square roots. There's no divide by zeros. We're not going to have any issues there. So we don't even need to consider that. Where is it equal to 0? And again, this is a polynomial with multiple variables, and the best way to solve those is to factor. So I'm going to factor out a -6x, leaving me with an x minus 2. Check your math, distribute it back in, -6x squared, positive 12x. All right, we're good. So what do we get? We get x equals 0 or x equals 2. So again, it's time for my first derivative sine chart. I have the values 0 and 2 as places where my slope is 0. So the question now becomes, what are the slopes everywhere else? So you've seen this process now a dozen times. We're going to take and plug a number in. So I'll plug in a really big number. You could plug it into your derivative up here. You could plug it into your factored version of your derivative, whatever is easiest. For me, I usually think about using the factored version. But in this case, it doesn't really matter. I plug in a billion or so, something bigger than 2. So this term takes over. It's positive times the -6. It becomes negative. So it appears my slopes are negative. A number between 0 and 2 would be like 1. And again, now I think about using the factored version. 1 in here makes negative. 1 here makes negative. A negative times a negative is a positive. Now I'm going to plug in a negative number, like -10 or something. And I get positive times negative, which is negative. So I'm going down, I'm going up, I'm going down. So again, I'm ready to answer some of my questions. When am I increasing? 0 to 2. Where am I decreasing? wherever my derivative is negative, so negative infinity to 0, or 0, no, 2 to infinity. Local max and local mins. Down then up, I have a local min at 0, comma, and again, what do? I want the y value, so I'm back up to the original equation. To plug in 0, I get negative 3. At 2, I have a local max. Plug in 2, do the math, get that answer. Okay, time for now the second derivative test. So I take my second derivative, and just like before, I want to find out when the second derivative is 0. So I have negative 12x plus 12 equals 0. Subtract 12, divide by negative 12. It appears I get x equals 1. Again, the second derivative is never undefined because it's a polynomial, so we don't even need to worry about it. I get x equals 1 as my only possible inflection point. So now I'm going to look at a second derivative sign chart. And this is essentially going to be my inflection point if it changes concavity. So we want to find out what is the second derivative doing. So I go in, I plug in a billion or so, and I get a negative number. So my second derivative is negative, and then plug in 0 or something else less than 1, and I get a positive. So a positive tells me in my second derivative that I'm concave up. So I now know I'm concave up from negative infinity to 1, or, nope, no or, we're done. Sorry, it's almost midnight, and I'm getting a little punchy here. Concave down when my second derivative is negative. So 1 to infinity. And therefore, do I have an inflection point? Yeah. It's at the point 1, comma, and again, we need the y value, so plug it in and get your answer. Again, where do I plug it in? What am I looking for? I'm looking for a y value, so I plug it in to the y. Okay, so let's just sketch what we kind of already knew about this graph and see if it matches what we found. I have a negative cubic function. So looking at a quick sketch of a negative cubic function, cubic function would look like this, and ours is going to be the opposite, so we should have something that looks like this. And I said it's increasing from 0 to 2, so yep, it's going up. Decreasing, negative infinity to 0, and from 2 to infinity. It's concave up from negative infinity to about 1. Yep. Concave down from 1 to infinity. Local max at 2, local min at 0, inflection point at 1. Again, as a rough sketch, matches up really well. So we'll stop this video here, and we'll do one more for now, and we'll finish the rest of them up another day.